Okay, YouTube, we've been using matrices, specifically augmented matrices, to solve systems of linear equations that have three or more variables. And up until now, we've been using this method called Gaussian elimination. In this video, we're going to confront what we call Gauss-Jordan elimination. And this also involves another mathematician's name here, Jordan, or Wilhelm Jordan. But basically, it just continues the process of Gaussian elimination even further in order to get what we say our matrix would be in reduced row echelon form. Okay, we want to get reduced row echelon form. So what you're going to see is that reduced row echelon form, remember that row echelon form, a little bit different than reduced row echelon form. Row echelon form was this where we had ones down the main diagonal and zeros elsewhere, and then we could have cared less what occurred over here on the top right, but we get this pattern here with reduced row echelon form. You could see that really our matrix would be in this form where we have ones down the main diagonal and zeros underneath them, but we also have zeros on top of them. And so you could see that this right here would require no back substitution. As a matter of fact, if these were, say, x variable, y variable, z variable in our constants, we could literally say that rewriting this system, we would say that x is equal to a, 1y plus no x's and no z's would be equal to b, and then 1z plus no x's, no y's is equal to c. We could see that our solution here would just be a, b, c, and that these would be the three constant values on the right side of our matrix, which is pretty slick, man. I want to go for this. I want to see how we could do this. So this process is very similar to Gaussian elimination, except for that extra set of steps here. So we would say that reading through this, essentially the same things that we're doing here, we're starting by writing the augmented matrix for the system, but then it says use matrix row operations to simplify this matrix into a new matrix that's row equivalent. It means the same solutions, but is in reduced row echelon form with ones down the main diagonal from upper left to lower right and zeros above and below the one. So the only difference is we don't have just zeros below, we have zeros above and below, and so are below and above. So what we're going to suggest is we'll still get a 1 in the top right corner, and we're still going to use that 1 in the first column to get zeros below it. So zeros below it. But then afterwards what it says is, part C, it says get 1 in the second row, second column, which is this entry right here, second row, second column. But then it says use the 1 in the second column to make the remaining entries in the entire second column 0. So the difference between Gaussian and Gauss-Jordan is it would have said here use the 1 in the second column to make the entries below it in that column 0, whereas Gauss-Jordan says make all entries above and below it equal to 0. And likewise, get a 1 in the third row and use that 1 to make zeros above it, not just, getting a 1 there. And then what we'll do is, this third step says use the reduced row echelon form of the matrix in step 2 to write the system solution set. But the neat thing is that back substitution won't be necessary because we'll already have the solution. So to take a look at what this would look like, Gauss-Jordan elimination, let's take a look at this system here that I want to solve, starting with writing its augmented matrix. So its augmented matrix would have coefficients 3, 1, 2, and then our first row would have a constant of 31 here. We'd say our second row looks like 1, 1, 2, and we have 19. And then our last row, we would have a 1, 3, 2, 1, 3, 2, and a 25. So now the first thing I notice here is that if I'm going to use matrices to solve this, I want a 1 in the top left corner. And so maybe what I'll do is I'll switch around row 1 and row 2. So looking at switching row 1 with row 2, let's go ahead and start by listing what we're doing here. We'd say I'm switching row 1 with row 2. And so row 1 now becomes 1, 1, 2, and 19. Okay. Row 2 now becomes 3, 1, 2, and 31. And our third row is still 1, 3, 2, and 25. So now that we have this 1, just as we do with Gaussian elimination, let's use the 1 to get zeros beneath it. So to get zeros beneath this, remember that our row operation we're going to use is that we're going to multiply that 1 by the opposite of these numbers and add it onto those rows. So that is to say, we're going to take row 1 times negative 3 and add it to row 2 to get rid of this positive 3. So we say negative 3 times row 1. Add that to row 2. And then the opposite of this positive 1 down here is negative 1. So we say negative 1 times row 1 here and add that onto row 3. What that's going to do is it's going to make sure that our row 1 doesn't change. We still have a leading 1. And it's going to make sure that these entries underneath it are zeros. So going through and kind of exploring these here, I suppose I'll get my calculator back out. If we took negative 3 times everything in the first row and added to everything in the second row, we get negative 3 times 1. So we say negative 3 times 1 plus 1, enter. We get negative 3 times 2, negative 3 times 2, plus now this 2. And we get negative 3 times 19, so negative 3 times 19. Okay, let's try this 19 here, plus the 31 in the second row. So plus 31. And so we would get negative 2, negative 4, and negative 26. Negative 2, negative 4, and negative 26. Now going back and taking everything in row 1 times a negative 1 and adding that to row 3, this is something we'd probably be a little bit more equipped to do mentally. We say the opposite of row 1 plus row 3. Well, we get negative 1 plus 1 is 0. Negative 1 plus a positive 3 would be a 2. Negative 2 plus a positive 2 would be a 0. We get negative 19 plus a positive 25 would be a positive 6. So now looking at this situation, we say, well, now what I want to do is I want to get a 1 here. So here's where it's going to start to diverge from what we're normally used to. Let's go ahead and take everything in row 2 times the reciprocal of negative 2 to make that a 1. So we would say, let's take this times negative a half in row 2. Row 1 is still going to be the same, 1, 1, 2, and 19. Okay. Row 3 is still going to be the same, 0, 2, 0, and 6. But row 2 is going to be negative 1/2 times 0, which is 0. Negative 1/2 times a negative 2, which is a 1. Negative 1/2 times a negative 4, which is a positive 2. And negative 1/2 of negative 26 is a positive 13. So you can see that now that we have this 1 here, this is clutch. What we're going to do is we're actually going to use this 1. We're going to use this 1 to eliminate the 1 above it and the 2 below it. So we're used to using this 1 just to kick out the 2. Now what we're going to say is a little bit different. We're going to say, let's do this. Let's take this 1 times a negative 1 so that when I add it to positive 1 up here, it cancels out. In other words, we'll take row 2 times this negative 1, which is the opposite of this positive 1, and add it to row 1. So we say row 2 times a negative 1, or negative 1 row 2, plus row 1. But we're also going to do this. We're going to say, let's take this 1 times a negative 2 to get it to cancel out with our third row here. So we're going to take row 2 times a negative 2. We're going to add that onto row 3. So you can see that row 2, by the way, it's not going to change. But you can see that we're going to go back and actually alter row 1 here instead of just row 3 or the row below or 1. So here's the neat thing about it. If you were to take negative 1 times everything in the second row, you already have a 0 here. And the reason why we already get a 0 there is because if you took that times a negative 1, 0 times negative 1, you get 0. And 0 plus what was already here, which is a 1, is still a 1. In other words, because we got a 0 here, it won't affect what we have above and below it. So don't worry about changing the progress you've made. We should have a 1 here. And so now going through the rest of this, we say a negative 1 times 1 here would be negative 1, plus a positive 1 would be a 0, what we wanted. And then we'd say negative 1 times this 2 in row 2, sorry, negative 1 times this positive 2 is negative 2, and negative 2 plus the 2 in the first row would be a 0. And then what we get is negative 1 times row 2, which is negative 1 times a positive 13 is negative 26, and negative 26 plus this positive 19 is, let's see here, negative 7, I think. Yeah, negative 7. So now, looking at row 3, we said let's take everything in row 2 times a negative 2, and then we'll add it on to row 3. So this means that we get negative 2 times 0 plus 0 is 0. Negative 2 times a positive 1 is a negative 2, plus a 2 is 0. Negative 2 times this positive 2 is negative 4. Negative 4 plus a 0 is negative 4. And negative 2 times this positive 13 is negative 26. And negative 26 plus a positive 6 is negative 20. So now our last goal will be this. Because we've got a 1 with zeros underneath it here in our first column, and then we got a 1 in our second row, second column with zeros above and below it. Now let's get a 1 in our third row here. And so we're going to take this times its reciprocal. We say negative 1/4 times row 3, first of all. So we get a 1, 0, 0, and a negative 7. Here we get a 0, 1, 2, and a 13. And then here we get a 0, 0, and then a 1. This would have to be a 1 after taking everything down here times a negative 1/4. Now negative 1/4 times a negative 20 is a positive 5. So at this point we could actually rewrite our system and do some back substitution, but our goal is now that we have a 1 here, we want to use this 1 to get the things above it to be zeros. And you can see that the only one we're going to have to change here is this 2 because we've already got a 0 here. So let me stretch this out. We don't have to go that high up. We would say let's take our 1 times a negative 2 and add it to this positive 2 to get it to cancel out. In other words, let's take row 3 times a negative 2 and add that to row 2 to get that to cancel. So rewriting our matrix here, we said we're going to take a negative 2 times row 3. We're going to add that onto row 2. So rewriting our entire matrix here, row 1, still the same, 1, 0, 0, negative 7. Our third row is still the same, 0, 0, 1, and 5. It was the second row we're operating on here, and what we get is this. I suppose if you took everything in the second row, or the third row times a negative 2, we already have 2 zeros here. So if you were to take those both times negative 2 and add them to the second row, it wouldn't change the fact that you have 0 and 1 here. Now if we take negative 2 times this 1 would be negative 2 plus a positive 2 is 0. And if we take negative 2 times this 5, which is in row 3, it'd be negative 10. And negative 10 plus a 13 in row 2 would be a positive 3. So what you're seeing now is that we would rewrite our system here. We would see that it's x equals negative 7. We'd see that 1y is equal to 3 and that 1z is equal to 5. This would be the system associated with this augmented matrix, but the beauty of this is that our solution, then, we already know our solution here to the system, and that must be an x value of negative 7, a y value of 3, and a z value of 5. So this is what Gauss-Jordan elimination looks like, and why it takes a little bit longer, but it's kind of beneficial because you save yourself the trouble of having to do back substitution when you're done. Cheers.